Welcome to UV Physics Academy. So here we are discussing the solutions of quantum computation. So this is our next question. Show that the tensor product of two positive operators is positive. Okay, so first let me define. In the earlier videos I discussed. So here positive operator means whose expectation value is positive. So here let me define two positive operators. Let us define two positive operators. Okay, so let us say this is A. So how I am defining this positive operators, let us say A cap and a B cap. So that means if I take the expectation value psi 1, A cap, psi 1, so this must be positive, either greater than or equal to 0. And the second one, for this B I am taking the state vector psi 2, a B cap and a psi 2. This is greater than or equal to 0. Now let us define the combined state psi, which is the tensor product of psi 1 and psi 2. Okay, so this in the Dirac notation we can write psi equal to, this is the ket psi 1 tensor ket psi 2. Right. Now we have to show that the tensor product of two positive operators is also positive. Okay. Now I am taking the tensor product of two positive operators. So for this combined state I am taking. Okay. Right. So this is a psi A tensor product B. Now I have to show that this is a positive. That means this is must be greater than or equal to 0. Okay, so let us proceed. Now already I have defined this a combined state as like this. So this is the bra psi. That's why I can write bra psi 1 tensor psi 2. Okay, so this A tensor B as it is. And after that this is the ket psi. That's why psi 1 tensor psi 2 ket vector. Now in the last videos also I explained the technique. If you have here three independent terms, simple, just take a first and here first. That means what is the meaning of this? Psi 1 and here it is A cap. So and the next one is again psi 1. Okay, and the tensor, the second terms, second and this second. So then it is bra psi 2, so normal product, B cap, and this is again a psi 2. Now we have already defined these two positive operators whose expectation value positive, and this is also positive. So since this is a positive greater than or equal to 0 and this is also greater than or equal to 0, so we can conclude that this must be greater than or equal to 0. What is that? Psi A tensor B psi. So we can say that the tensor product of two positive operators is also positive, right? So the next question, show that the tensor product of two projection operators is also a projection operator or projector. Okay, so here I am defining two projection operators. Let us define two projection operators or two projectors, whatever they have given. So let us say P1 cap and P2 cap. So these are projection operators. You know already the properties of a projection operators. That is a P dagger, it's a Hermitian, P only, and a P square, it's idempotent, and this is a P square equal to P. Okay, so now we know this. These two are the projection operators. That's why P1 square equal to P1, and as usual P2 cap square equal to P2. Now we are taking the tensor product of these two projection operators. Okay, so tensor product of two projectors, So what is that, a tensor product of two projectors? Just we can write it as a P1 cap tensor a P2 cap. Now we have to show that this is also a projector or projection operator. So for that I am taking this P1 cap tensor P2 cap. Now I have to show that this is a projection operator. So just take square, which is nothing but, if I will get the same, that means P1 tensor P2, then it is also a projection operator. So this can be written as P1 tensor P2. So one more time multiply P1 tensor P2. So I told you in the last class the rule, whenever you have A tensor B operators and here C tensor B, something like this, CD, just do the ordinary multiplication, scalar multiplication, AC, and tensor this second, that is BD. So this is the scalar multiplication and this is also scalar multiplication, and here again you will get the tensor. So by using that property, first that is a P1 which is a P1 square tensor, second into second scalar multiplication, P2 into P2 square. So we know P1, P2 are the projection operators. That's why again we can write P1 cap tensor and this is nothing but P2. So finally we got P1 tensor P2 whole square equal to P1 tensor P2. So product of two projection operators is also a projection operator. So this is our next question. So this is very crucial and a lot of applications in the algorithms also. So here they are asking to show that the Hadamard operator of one qubit, single qubit, can be written like this. This is the first one. And after that they are asking the general representation, the Hadamard operator operating on n qubits, that means a H tensor n. So this they are asking. And the next explicit matrix representation for H tensor 2, that means this is for 2 qubits. Okay, so let us do this problem in two different ways. Okay, so first let me take first method. This is the first method, method 1. So what is this? Now if you want to get this, if you observe carefully, here we are having a ket and here we are having some bra notation, something like this. Okay, so there is one minute. Okay, fine. So let us start. Now let me take the method 1. Okay, so here I am using this outer product form. So any operator can be written in the outer product form like this. So this is the outer product form. So here we will take psi initial and here we will take psi final. So otherwise you can take this as just like input and this is the output. So here we are discussing about the Hadamard operator. So whenever Hadamard operator, this is the single qubit. Okay, so Hadamard operator operates on 0, you will get a diagonal basis. Computational basis are transformed to converted to diagonal basis, and similarly H operates on 1, you will get the minus. Okay, so according to this I can write the Hadamard operator equal to, so what is my input? This one, ket 0. The corresponding output is what? Plus in bra vector, plus next one, what is the input here? 1, and the output minus, that is the diagonal base. So I hope you know what is this plus and minus. The diagonal bases are nothing but the linear combination of computational basis, ket 0 plus ket 1 here, and this minus, which is 1 by root 2 this is 0 minus 1. Okay, so now I'm going to substitute this plus, which is 1 by root 2 ket 0. So this is 0 plus 1 here. Okay, so that's it, and plus 1 here, and here this is the bra vector of minus, that is a 0 minus 1, and here 1 by root 2, one more is there, that's why I'm taking this as 1 by root 2 whole square. 1 by root 2 whole square. Okay, fine. So finally we got the head mod. I'm sorry, just a common, extremism. So here it is a 1 by root 2, and here also 1 by root 2, just to take that 1 by root 2 common, no need to multiply, sorry. So after that we got head mod operator h equal to 1 over root 2. So just I am splitting this is a ket 0, okay, and after that it is multiplied with bra 0 plus bra 1, something like this, plus, and here it is a ket 1, and multiplied with bra 0 minus 1. That's it. Just I have written this one, just I split this bra vector. Now I'm going to multiply, so which is a 1 by root 2, just multiply, this is the outer product 0 plus outer product 0 and 1 plus outer product 1 0 minus outer product 1 1. So if you want to get this this form, maybe here if you observe carefully, maybe our input and output are a reversal here, but okay, we can get back to this. You just take the common, so we can get that form again. So if you observe carefully, here we have a plus 1 plus state, and this is a bra 0. So here what I'm doing is I'm just taking common bra 0 and this bra 0, then it is ket 0 plus ket 1 bra 0 plus, and similarly I'm taking this common bra 1, so then it is again ket 0 minus ket 1 into this bra 1, something like this. So we got this form. So this is one way. If you feel this is a little bit complicated, okay, so then we can try in another way also. Now it's very simple. Now here we have head mod operator. So head mod operator is a 1 over root 2, 1 1 1 minus 1. Now first write in the matrix representation. So whenever you are writing the matrix representation, you need the basis. Here my input and output bases are computational basis, okay, so that's why a 0 1 and here also a 0 1. So let me write this matrix 1 1 1 minus 1. Now you want to get the output, outer product form. It's very simple. Just take the element as a coefficient and write the corresponding bra as a ket and a ket as a bra, because we have to get the outer product form. So very simple. Take the matrix element corresponding to that, whatever you have ket and bra, just reverse it. That means make the bra as a ket and make that a ket as a bra. So see, we can write this as head mod operator h is equal to, of course here 1 over root 2 outside. Now see how simple it is. Here coefficient is 1, so this is the bra, just to make it ket, and this is a ket and make it a bra. And the next plus, here I am taking this one, plus 1. Corresponding to this is the bra, make it ket, and this is the ket, make it bra. And the next I am taking this one, this element, third element. Here a bra is 1, make it ket, and this is a 0. And finally here we have minus 1 element. This is becoming ket, and this one is a bra. So finally here we got the same expression as earlier, h is equal to 1 over root 2. So outer product 0 and 0 1 and plus 1 0 and minus 1 0. If you check this, we got the same answer. I mean here. Okay, right. So here we have used the technique from that matrix representation, and here we have used this rule, and this is valid for any operator. If you want to write any operator in the outer product form, so just you have to take a summation, combination of these outer product form, but here ket input and output is in the bra vector. I think this is a little bit easier than that. Okay, fine. So again you can take common here, bra 0 and this one also. So we got whatever he asking in the question, so we got that. If you take common, sorry, I think here this is a 1. So this is bra 1. That's it. So this is what he is asking in the first part. Okay. Next, after that, he is asking to generalize this for 2 qubits, 3 qubits, and n qubits. Okay. So for this, I am taking this expression only again. Okay. So yeah, clear this because you understand already how you got that. So please carefully observe this. Here we have coefficient +1, +1, +1, and here it is a -1. So this can be written as, h can be written as 1 over root 2. No doubt this is the outer product, let us say xy. And let us suppose this x and y are binary strings. That means 0 or 1 for single qubit. If it is a 2 qubit, 0 0, 0 1, 1 0, 1 1 like that. 3 qubits, 0 0 0 2, 1 1 1 1 1. These are binary strings. And here how to get this coefficients? If you observe carefully, here we got +1, here we got +1, here +1, and here -1. Okay, here it is easy, 1 into 1, okay, we got here minus, and this product is a 0, this product is 0, this product is also 0. So we can write this as -1 whole power x dot y. But remember, this x dot y is the binary product, mod 2 product. So what is the meaning of this? So for example, see, here we have 2 qubits, let us say 1 1. I'm making the dot product with the 1 1. I told you already x and y are binary strings. Okay, so here I have taken 2 qubits. Just like a dot product, first term into first term, second term into second term. So that is 1 into 1 1 plus second 1. But you have to take modulus 2. Right? So this is a 2 mod 2, so which is nothing but 0. If you take 1 1 1 dot 1 1 0, for example, 3 qubits you have taken. So simple, this is also. So first 1, second into second 1, plus third into third 0. Again it is equal to 2. So but you have to take a 2 modulo 2. So which is again equal to 0, like this. So and after that here we have to take the summation over x comma y. So what are these x comma y? So here it is a single qubit, that's why it's simply 0 comma 1. So we can rewrite this summation, this series, this one as a summation form like this. Now let us take 2 qubits. If it is a 2 qubits, we will get the similar, quite similar one. Okay, so this is a 1 by root 2. You will get a whole square because 2 qubits, summation minus 1 whole power x dot y, binary modulo 2 product, and this is xy. But this time this x and y are binary strings, but 2 qubit binary strings. Okay, so that means here x comma y equal to 0 0 or 0 1 or 1 0 or 1 1. Sometimes we can write like this also, 0 comma 1 2. That indicates this is a 2 qubit binary strings. And if you generalize this, and we can write for n qubits. Okay, so quite similar. Just take a 1 over root 2 whole power n, 1 over root 2 whole power n, summation as usual, minus 1 whole power x dot y, and this is the outer product xy. But this time your x comma y belongs to, you can write like this, 0 comma 1, and here you can write like this, or some, I think yeah, it's okay, whole power n or tensor n, okay, whatever it is. I think some people will follow that whole power n also. Okay, so that's it. So this is the more general representation of Hadamard operation on n qubits. So this is what they are asking. Okay, if you have any doubt, so please contact. Right, so here this is the next question, and they are asking the square root and the logarithm of this matrix 4334. This is also very interesting question. Okay, so if you want to find the square root or logarithm or sine or cos or whatever it is, some function of a matrix, first we have to find eigenvalues and eigenvectors, and after that we have to apply the spectral decomposition method. Okay, so first let me find eigenvalues and eigenvectors of the given matrix. Eigenvalues and eigenvectors. First let me find eigenvalues. So the given matrix is 4 3 3 4. So let us do the original method. So here we have the secular equation, sorry, characteristic equation, lambda square minus trace lambda plus a determinant equal to 0. So then this is the lambda square, a trace is nothing but 8, and a determinant, this is a 16, and this is a 9 plus 5 equal to 0. And if you solve, you will get this lambda. And there is one more technique. What is that? So whenever your matrix is in the form of A, B, B, A, if you observe carefully, diagonal elements are same and this off diagonal elements are same, then this is nothing but eigenvalues are simply A plus R minus B. That means one is A plus B, another is the A minus B. So according to this, we will get 4 plus 4, 8, and 4 minus 3, that is a 1. So you will get 1 comma 8. Sorry, 1 comma 7. I'm sorry. One is 4 plus 3, 7. Another is 4 minus 3, 1. So you will get 1 comma 7 are the eigenvalues. Okay. So this is a small technique. Use this 1 comma 7. Now for these eigenvalues, now I am going to find the corresponding eigenvectors. Right. So first I am taking lambda equal to 1. Now let us say eigenvalue equation A psi equal to lambda psi. My A is 4 3 3 4, and this is a psi xy, and this is a 1 xy. So I told you earlier also, one equation is enough. This is a row and a column. So this is a 4x plus 3y equal to x, which implies 3x is equal to 3y. sorry, 3x plus 3y equal to 0, which implies y equal to minus x. Always better to write y in terms of x, then immediately you got the wave, the eigenstate corresponding to this lambda equal to 1 as x comma minus x, sorry, x comma minus x, that means x minus x. And if you take the normalization constant, so finally we got for lambda equal to 1, we got the eigenstate psi 1 equal to 1 over root 2 1 1 1, sorry, 1 minus 1, because y is here it is a minus x, put 1 here, 1 minus 1, like that. Second one you please try, okay. So if you take lambda equal to 7, next eigenvalue, because this is a minus b1 and a plus b 7, you will get a second state psi 2 equal to 1 over root 2 1 1. So I request you to please try this second state. So once you got your eigenvalues and eigenvectors, and you can write by using this spectral decomposition. So the matrix A can be written as a summation over I. So lambda I, this is the psi I, psi I. That means again the linear combination of outer product, but this time this outer product is eigenvectors. These are eigenvectors, and these are the eigenvalues. Okay, so here first we got our eigenvalues and eigenvectors corresponding to the given matrix. Now how to write this square root of that matrix and a logarithm, let us discuss. So one more time I am taking these things, okay. So here I have matrix A, which is 4 3 3 4. I got lambda 1 equal to 1, and corresponding to this psi 1 equal to 1 over root 2 1 minus 1, and the next lambda 2 equal to 7, and I got the wave function psi 2 equal to 1 over root 2 1 1. And after that this is the matrix A, which can be written as summation over I lambda I, the outer product of these eigenvectors. So from this we can write our matrix A equal to the first eigenvalue 1, so this is a 1, and after that this one psi 1 outer product. Next eigenvalue is a 7, and outer product psi 2. So please remember this is a very crucial. That is our given matrix representation in the outer product form. Okay, fine. Now let us come back to this required thing. So what he is asking the square root of that matrix. Okay, so you know one thing, whenever there is a matrix A, we have eigenvalues lambda 1, lambda 2, lambda 3, so on, and the corresponding eigenvectors psi 1, psi 2, and so on, psi 3, so on. Then what about the eigenvalues of A power m? The same, same means lambda 1 power m, lambda 2 power m, lambda 3 power m, so on. And eigenvectors are same. No change in the eigenvectors. So similarly, if I take square root of A, that implies I got root lambda 1, root lambda 2 in this case. And the corresponding eigenvectors are same, psi 1 comma psi 2. So I will write there, I need space here. So by using this technique, we can write the eigenvalues of root A are simply root lambda 1 comma root lambda 2. But the corresponding eigenvectors psi 1 and psi 2. Eigenvectors are same, only eigenvalues are changing. And similarly log A, Here also we have log lambda 1, log lambda 2, but eigenvectors are same, psi 1 and psi 2. Now it's very simple. Now first I am writing my matrix, given matrix A in the form of a spectral decomposition. 1 psi 1 outer product plus 7 psi 2 outer product. Now I want square root of A. So this is, I told you already. So whatever root lambda 1 eigenvector is the same. So otherwise here also please write in terms of lambdas, and there will be no confusion. And here root lambda 2 psi 2 psi 2. Now just substitute these things. Now root lambda 1 which is equal to 1, and this is the outer product of psi 1 psi 1. This is my psi 1. It's a ket vector 1 by root 2 whole square, because the ket and bra are there. So this is a 1 minus 1 column matrix. This is the bra vector 1 minus 1 row matrix, plus root lambda, square root lambda 2. This is a root 7, and again here outer product which is 1 1 and 1 1, and here I can take this 1 by root 2 whole square common. So finally if you simplify this matrix, you will get 1 by 2, and this is nothing but 1 minus 1 minus 1 1 plus, and here it is root 7 by 2 into 1 1 1 1. So this is nothing but 1 plus root 7 minus 1 plus root 7 and minus 1 plus root 7 and 1 plus root 7, and this whole by 2. So this is our final answer. This is the square root of A, just write like this. So the next he is asking this one logarithm. Okay, so I hope you understand. If you have any doubt, please contact. Okay, right. The next we want to write log A. So by taking the same rule, eigenvalues you will get, eigenvalues will be changed, but eigenvectors remains the same. So this is a log lambda 1 outer product psi 1 eigenvector plus log lambda 2 psi 2. Okay, now this is the first eigenvalue is 1, that's why this is a 0. Log 1 psi 1 plus log 7 psi 2 psi 2. So this is a 0, and then just we remain with log 7. Log 7, this is the outer product psi 2 psi 2. That's good. Now finally we can write this as a log 7, and this outer product is 1 by 2, of course. Okay, so let me write like this. I will write 1 by 2 here, and log 7, and this is 1 1, because this is the column matrix, and here 1 1. So finally here we got log 7 by 2, and this is 1 1 1 1. So this is our log A matrix. So this is a beautiful concept. So spectral decomposition, like this we can find sign of that matrix, sin A, cos A, so anything we can find. Right. So let us go to the next question. So this is a very, very important question for our quantum computation. So let V be any three-dimensional unit vector, okay, and theta is a real number. So they are asking to show that exponential iota theta V bar dot sigma equal to cos theta I plus iota sin theta V dot sigma. This is a very important. Okay, so let me do in two different methods. So whatever the method you understand, you please take. Okay. So first, let me go to the mathematics expression. So I hope everybody know one thing: e raised to x expansion by using this Maclaurin series or Taylor series at the origin. E raised to x is equal to, so 1 plus x square by 2 factorial plus x cube by 3 factorial, so plus so on. We can write this as a summation x power n by n factorial, where n equal to 0 to infinity. This is e raised to x expansion. Whenever you are having operators here, this one is replaced with the identity and these things are replaced with the operators. But in our question, this is our e raised to, this is e raised to iota theta v dot sigma. But remember, this v is a unit vector. So unit vector means here this v bar is a unit vector, three-dimensional unit vector. So what is the meaning of this? So its magnitude is equal to 1. That means v1 square plus v2 square plus v3 square equal to 1. Okay, fine. So if you want to proceed with this, I think here in the expansion you will get like this, which is because of the operator, I am taking I plus x. This entire thing is my x. So that's why I can write iota theta v dot sigma. Just replace in the place of x this entire thing, just replace. Okay, and the next iota square is there, that's why minus, and theta square as usual by 2 factorial and v bar dot sigma whole square. Next cube is there, iota cube is minus iota and theta cube, just take this as x and substitute here. So by 3 factorial, so v bar dot sigma whole cube, so on. So in this we have to find what is this v dot sigma whole power n. That means whole power 1 how much, whole power 2 and whole power 3 how much. So for this let us take more generally. I am talking about this v bar dot sigma. Okay, so what is this v bar dot sigma? Let us take v bar dot sigma whole square, because v bar dot sigma whole power 1 is the same. So let us talk about whole power 2. So this can be written as whole square is nothing but, so we can write this as vi sigma I. I mean in the tensor product form I am writing, I mean tensor notation, I'm writing in the tensor notation. Whenever you have these two, a dot product, we can write it as a vi sigma I, and whole square is there. So that's why that means this is nothing but v bar dot sigma and again v bar dot sigma. So in the tensor notation we can write this, this is a vi sigma I and this also vj sigma j. Just take a dummy index, another dummy index. Okay, so finally we can write this as vi vj and sigma I sigma j. Right. So next what we have to find is this one, and I'm doing more generally. Okay, so this is the tensor notation. If you don't know the tensor notation, please inform me. So I will make one more video on this tensor notations and how to find the dot product, cross product. Okay, so if you know, it's okay, otherwise please inform me. Right, so now I'm going to find this sigma I sigma j. Ready? So what is this sigma I sigma j? For example, if you want to find sigma I sigma j, first let us talk about I equal to j. Then it is a sigma I square, which is a sigma x square, sigma y square, sigma z square, which is identity. So if these two are same, we are getting identity. Means sigma I square is always identity. If not same, then what we will get? Generally, if you take the product sigma x into sigma y, you will get iota sigma z. If it is in the order, so cyclic order, x, y, then you will get z. If it is in the reverse order, sigma y, sigma x, it is a minus iota sigma z. So, if it is in the order, we will get iota sigma z. If it is in the disorder, we will get minus iota. Okay. So, I think this can be obtained from Levi-Civita symbol. So, more general form, how I am writing, the sigma I, sigma j equal to, if both are equal, both indices are equal, I will get I, identity. So that's why I am using a Kronecker delta, delta ij I. So that term makes, if I equal to j, then it is I mean identity. And the second term, if I equal to j, it must be 0. So that Levi-Civita is having this property, that is represented by epsilon ijk. Epsilon ijk. So in this epsilon ijk, if it is in the order, +1, if it is in the disorder, -1, and if any two are same, it is a 0. Oh, it is having a 3 values. So +1 for order, -1 for disorder, 0 for any two are same. So iota is as usual, plus, and after that, if you observe carefully, x and y, we are getting z. Okay, that means I and j. So what is the third one? That is sigma k. So this is the general form of a product of sigma I, sigma j. If you have any doubt, so please contact. Okay, so this is a Levi-Civita and this is a Kronecker delta. This is a Kronecker delta and this is a Levi-Civita. Levi-Civita. So +1 for order, -1 for disorder, that means cyclic permutations and anti-cyclic permutations, and this is 0 for any two are same, any two are same. See, if any two are same means if I equal to j, this term is completely 0, then we are getting I. And order, we are getting iota sigma z, disorder, we are getting minus iota sigma z. So this is the more appropriate, more general form of product of 2 Pauli spin matrices. That's good. Okay, so if I take this, now, sorry, again I am taking this v bar dot sigma whole square I am finding, whole power 1 no need to find. So finally here we got vi, vj. So this is a sigma I, sigma j. Right. Now this product, already we got, what is that? Sigma I, sigma j equal to, this is delta ij, okay, it's not iota, ij, I, plus this is iota. Don't be confused with this I and this I. This is the index and this is the iota. Epsilon ijk, this I and this I both are same, careful, and this is a sigma k. That's good. Nice. Okay, so now just take it and substitute. So vi, vj, and this is nothing but delta ij, identity, plus iota, epsilon ijk, and sigma k. Now just multiply, split it. So vi, vj, delta ij, I, plus iota outside I am writing here, vi, vj, epsilon ijk, and a sigma k. Now carefully observe. I told you here we are using the tensor algebra. If you don't have, if you have an idea, it's okay. Otherwise, please ask me. Please inform me. Definitely, I will prepare one more video on that tensor notations and a tensor algebra. Right. So here, this is a non-zero only when I equal to j. So that's why this can be written as a simply, this is nothing but a dot product actually. So this is the dot product notation. So v dot v, or simply we can write v square. Okay, so this is identity as usual. Okay, and identity plus, I mean v square means the magnitude, v square magnitude, plus this one, what is this? This is the cross product. This is the dot product and this is the cross product. This is a v bar dot v bar into I, and this is the cross product, v bar cross v bar. Okay, that too, which component means it is the k component or something like this. Okay, and here we have sigma k, of course, and you know one thing, a bar cross a bar, so cross product of the same vector, this is always equal to 0. One more time, so if you don't know this notations, please ask. And this is nothing but v square I. And already I told you, I mean in the question it is given, v is a unit vector in the 3 dimension. So if you observe carefully, if you take a v square, this is the magnitude of v. If you take its a square, then you are getting 1. So this v square is equal to 1. How much it is? I. So finally we got this result, v bar dot sigma whole square equal to I, identity. So finally we can conclude like this. If it is a whole power n, sometimes n may be even or sometimes n may be odd. So here we have v bar dot sigma whole power n. So this is v bar dot sigma, again if n is odd. For example, let us take whole cube. Whole square already become identity. So that's why again you will get the same. So if it is an even number, so this is simply I if n is even. Now everything, whatever we need for this problem we got. So here we have the expansion. We have to substitute this and this whole square, whole cube, whole power 4, so on. Okay, so let us go with that. E raised to iota theta v bar dot sigma bar equal to identity plus iota theta v bar dot sigma, and after that minus iota square is there, theta square by 2 factorial, and this is a v bar dot sigma whole square which is equal to I, minus iota theta cube by 3 factorial, and v bar dot sigma whole power 3 which is equal to v bar dot sigma, and so on you can take. Now here what I am doing is just I am taking common I, identity, then what you will get. So this is if you take I common 1 minus the theta square by 2 factorial. If you proceed further, it will be theta power 4 by 4 factorial, so on into I. And the next what I am taking common, so I am taking common iota, okay, and a v bar dot sigma bar also I am taking common. Then what I will get here, theta minus theta cube by 3 factorial, so plus theta power 5 by 5 factorial, so on. So into v bar dot the sigma bar. So anywhere you can write this here, so nothing will happen. So I hope everybody know this is the Maclaurin series of cos theta and I plus iota, and this is the Maclaurin series of sine theta. So sine theta, and after that v bar dot sigma bar as it is. So this is the e raised to iota theta v bar dot sigma bar, where v is a unit vector in a 3 dimension. So this is what we have derived. So this one. Fine. So here if you feel this is a little bit lengthy algebra, so let us do it in another way also. Okay, so here we have to show this e raised to iota theta v bar dot sigma equal to cos theta identity plus iota sin theta v bar dot sigma bar. This is what we have to discuss. Let us do in another way by using spectral decomposition. For that, if I want to find the spectral decomposition of this, actually this is easier than that method. Of course, this is also easy, but maybe you feel little bit lengthy, and here we have used this tensor notation and all these things. Okay, so ready. If you want to write the spectral decomposition for this, first I have to write the spectral decomposition of this matrix. So let me find v bar dot sigma matrix, which is nothing but v1 sigma 1, that means sigma x, v2 sigma y, we can write sigma 2, okay, sigma 2, and v3 sigma 3. So if you substitute your sigma x 0 1 1 0, 0 minus iota 0, let me write that also, 0 1 1 0, and plus v2, this is a 0 minus iota 0, and plus v3 1 0 0 minus 1. If you just add these matrices, there is no difficulty at all. Just if you add, here you will get v3, and here you will get minus v3, and this off diagonal you will get here v1 minus iota v2, and here you will get v1 plus iota v2. That's it. So this is my v bar dot sigma matrix. Okay. So once I got this matrix, for spectral decomposition, I have to find eigenvalues. Eigenvectors no need to find, just find eigenvalues. So this is v3, v1 minus iota v2, so v1 plus iota v2, and this is v3. Now, oh sorry, here it is minus. Okay, how to find the eigenvalues? I told you already one method, trace. Trace is a 0, and a determinant. Determinant is here, we got this one, minus v3 square, and minus v1 square, and after that we got here of course minus v2 square again. So which is nothing but a minus of v1 square plus v2 square plus v3 square. So you know this v is the unit vector already given in the question. So here this unit vector, okay. So that's why this magnitude is equal to 1, and this is a minus 1. Fine. So we got the determinant minus 1. That's why lambda square characteristic equation plus a determinant equal to 0. So trace is 0. That's why lambda square. Determinant is minus 1 equal to 0. Lambda equal to plus or minus 1. But no need to do this also, because eigenvalues, that is a measurement of Pauli spin matrices, independent of the orientation, independent of the direction of measurement, not orientation, direction of measurement. That means if you have a sigma bar, that means S bar or sigma bar or something like this, just come out of this question and let us discuss more generally. So this is X and Y and Z. So this is your sigma bar, or spin vector S bar also you can take, because S and sigma are related by H cross by 2 sigma, Si sigma I. Whenever you are measuring this sigma along x-axis, so this is x-axis and this is y-axis. Along x-axis, that is nothing but sigma x. What is a sigma x? This is nothing but sigma bar dot x cap. If you measure the sigma along y-axis, what is that? Sigma bar dot y cap. If you measure the sigma along a z-axis, which is nothing but a sigma z is nothing but sigma bar dot z cap. So this is a sigma z, and this is a sigma y, and this is a sigma x. We know all Pauli spin matrices are having eigenvalues of plus or minus 1. Once you make a measurement, you will get lambda equal to plus or minus 1 along x-axis, I mean, you measure along this x-axis. And here also lambda equal to plus or minus 1, and here also lambda equal to plus or minus 1. So we can say one thing, this is independent of direction of measurement. So finally we can say like this, sigma bar dot n cap eigenvalues, lambda of a sigma bar dot n cap is also equal to plus or minus 1. So if you take lambda of s bar dot n cap, this also plus or minus h cross by 2. That means Sx, Sy, Sz, S bar dot n cap all are having the same eigenvalues, so that is a plus or minus h cross by 2. Okay, so but this is not related to our question, but I will keep this. If you have further any clarification, you can go through this. Now let us proceed to our problem, right? So we got the eigenvalues plus or minus 1. Okay, so this is the matrix we are discussing. So finally, V bar dot sigma bar, I can write it as a spectral decomposition, summation over I, lambda I, outer product of this eigenvectors. No need to find the eigenvectors, leave it, because eigenvectors are same. Already earlier problem we have discussed for a, log a and a power m, eigenvectors are same, eigenvalues are different. So here first eigenvalue we got plus 1, another one is minus 1. So I can take plus 1, just psi 1, that's enough. Minus 1, psi 2. That's it. This is my V bar dot sigma matrix. Now I want this e raised to iota theta V bar dot sigma. Okay. So for this, I have to find the eigenvalues of this. Am I right? Yeah, eigenvalues of this. Or we can write it directly if you understand already. Here it is lambda I, and here it is e raised to iota theta lambda I. That's it. Okay. So A is having eigenvalues lambda 1, lambda 2, lambda 3. Then e raised to A is having eigenvalues e raised to lambda 1, e raised to lambda 2, e raised to lambda 3, so on. The same technique. And this is psi I, psi I. So we know what is a lambda 1 plus 1. That's why this is e raised to iota theta, psi 1, psi 1. And the next one lambda is minus 1. Don't write minus here. Be careful. So lambda is here, not here. Okay. E raised to minus iota theta, psi 2, psi 2. Now see, it's very simple. So maybe I explained this concept in the middle, that's why you may feel it's lengthy, but this is not at all related to this question. But it's a very useful concept, more general concept, okay? Right. So we know what is this e raised to iota theta. What is e raised to iota theta? Cos theta plus iota sin theta. This is psi 1, psi 1 plus this one cos theta minus iota sin theta, this outer product psi 2, psi 2. Okay, now I am taking this cos theta common. So then I will get, if I take cos theta common, I will get this outer product psi 1 plus psi 2, psi 2. I hope you know this, our earlier classes we have already discussed. This is nothing but identity matrix whose eigenvalues are 1, 1. Okay, lambda 1, lambda 2. So same input and output bases are same. So this is nothing but identity. So this time plus iota sin theta I am taking common. Then I will get, what is this? Psi 1, see carefully this one, psi 1. And here it is a minus because I am taking a iota sin theta common, minus this one I will get. Right. Now if you observe carefully, so here this last one, this is nothing but our V bar dot sigma. So this is V bar dot sigma. So we got e raised to iota theta V bar dot sigma equal to cos theta identity I plus iota sin theta V bar dot sigma bar. So this is a beautiful expression. If you have any doubt, so please contact. So here I didn't use any tensor notation. Maybe I hope you feel this is a little bit easier than that earlier method. Right. So let us go to the next question. So here they are asking, show that Pauli matrices except identity have trace 0. So let us take straightforward. Okay. So the Pauli matrix is X 0 1 1 0. So trace is nothing but the sum of diagonal elements. Okay. So trace of X is nothing but summation over I A I ith row ith column. That means diagonal elements. So which is equal to 0. And if you take Y, this is also 0 minus iota 0. So trace of Y, any matrix is a sum of diagonal elements ai, which is equal to 0. And Z, so this is a 1 0 0 minus 1, and here also the trace of Z is equal to summation over I ai, which is equal to 0. If you take the identity, so this is 1 0 0 minus 1, sorry, plus 1 1. And here if you take the trace of I, which is a summation over I ai, which is equal to 2. Right. So this is a trace of, that means we can say trace of sigma square is a 2. Trace of sigma x square, or trace of y square 2. Trace of z square is also 2. I think we can write like this more generally. What is that? If both are same, we are getting 2. Otherwise, both are different, we are getting 0. I think shall we write like this? A trace of sigma I, sigma j equal to, shall I write this 2 delta ij? Because if I equal to j, I'm getting a 2. If I is not equal to j, I will get a 0. Okay, that's it. Right. And the next question is about, if A and B are two linear operators, show that trace of AB equal to a trace of BA. Okay, fine. Now, first let us write how to write this trace. Trace of any matrix is the sum of diagonal elements. What are diagonal elements? A11, A22. If A is the matrix, A22, A33. What are A11 and A22, A33? Matrix elements. So we can write this trace of A, B, where A and B are two linear operators. We can write this as a summation over I. So matrix element, ith row, AB, ith column. So this is the sum of ith row, ith column elements of AB. That's the meaning of this. Earlier we have written like this, but here we are writing the this bracket notation. Okay, so now I am using this completeness rule. So I hope you remember completeness rule. So I'm taking another dummy index, so summation over j. So this is j outer product equal to I. Just take it. Now here I am going to write this as a summation over I, and I am writing A, I, B. Here I am writing identity. Okay, so because I have to interchange these two. So just to take that I and substitute here. Summation over I. This is the summation over j. We can write it outside also, it's not a problem. So summation over j, I, A. So this is nothing but j outer product, and B and A, ket vector I. Now carefully observe. So you just split this. This is nothing but summation over I, summation over j. This is I A j, sorry, and this one j b and I. Okay, fine. So here this is the matrix element only, which is the scalar. So that's why what I'm doing is just I'm interchanging these two. So this is a summation over j, a summation over I. Just interchange these two, j b I. Carefully observe. And again this is I, A and J. So whatever the technique earlier we have used, this one, identity, just if you observe carefully, I am bringing this summation over I here, then it will be summation over I, outer product II, which is equal to identity matrix, and we got this is summation over J. Okay, so see here summation over J, and this J is as it is. Okay, and here B is also as it is, and summation over I, outer product I, and again this is A as it is. Okay, so now this is nothing but identity. So this is the summation over J, J and B, identity A, which is nothing but BA. Just J is some just a dummy index, so that's no need to worry about this. And this is also nothing but trace of BA. So we can show that the trace of AB equal to trace of BA. And the next one, A and B are two linear operators, and show that trace of A plus B equal to sum of individual traces, and a trace of constant into matrix equal to constant into trace of that matrix. Okay, this is also very simple. If I take a trace of A plus B, just I am using the same notation, sum of diagonal elements, summation over I, diagonal element, ith row, A plus B, ith column. So that's it, and just split it, nothing else. Summation over I, A, because these are linear operators, I plus I, B, I. So which is nothing but the first one is nothing but a trace of A, and the second term is nothing but a trace of B. So finally we can say a trace of A plus B equal to the sum of individual traces. And the next one you can try yourself. This is also easy. A trace of ZA, where Z is a constant, a complex number. This Z belongs to some complex number. Now this can be written as trace of ZA equal to, okay, again sum of diagonal elements, ith row, ZA. A is a matrix. To indicate that I'm placing the cap there. So to indicate this is a constant and that is a operator. So you can bring this a constant out. So no issue. Z, a summation over I, A, I. So this is nothing but a trace of A. So Z into a trace of A. That's it. So here, this is our next question. This is also very important property of a Pauli spin matrices. Okay, the first one is very simple. By using the matrices, we can easily prove that. That's not a problem. But the second one is you need that tensor notation knowledge. Okay, so first let us do this matrix product. Okay, now I'm taking this Pauli matrices X 0, 1, 1, 0, and this Y 0 minus iota, iota 0, and Z, this is 1, 0, 0 minus 1. Now this is a commutator X comma Y. The commutator definition is simply xy minus yx. So I am using this technique here while I am multiplying these two matrices. I am not multiplying with the original method. So in my earlier one, there is one series of lectures on quantum computation. So please go through that quantum gates lecture. So there I explained some techniques to multiply. So here x is operating on y. So what is x? 0, 1, 1, 0. So how this matrix is different from identity? That means by interchanging the rows or columns, we will get I. How we will get back to I? So if you interchange the rows 1, 0, 1, 0, that means you will get again identity, or columns, you will get that identity. I have clearly explained there, so I request you please see that. Otherwise, you can multiply the general matrix method also, but here I am writing a little bit more directly. So whenever x is operating on y, it's just interchanging rows or columns, but it is on right side, so that's why interchange the rows. That means iota 0, 0 minus iota means interchanging the rows of y. But see here, and x is operating on this side, so that is not the right side, so that's why you have to interchange the columns. Minus changing the columns of y, so that is nothing but minus iota 0, 0 iota. And if you just subtract, here you will get a 2 iota, okay, 0, 0, and minus iota, minus 2 iota, which is nothing but 2 iota, and this is a 1, 0, 0, minus 1, which is the Pauli Z matrix. So 2 iota Z, this one. So similarly, we can show this. You please try this y comma z. So easy only. So no need to get tension. Yz minus zy. So if you still didn't understand that writing directly, so I will explain for this also. See. Now instead of y, better to take z, because the z is similar to identity, but only here this second row or second column is having a negative sign. So what I will say, whenever you are multiplying any matrix with z, you will get the same matrix, but a second row or a second column is multiplied with minus. So but more clearly I explained there in that video. So if you have time, please see. Okay. So this is a z is operating like this. So this side, it's not the right side. That's why column change. And see, this z is operating like this. So this is which side? A right side. So here what I'm saying is, you will get the same y, because the z is multiplying with the y here like this. You will get the same y, but that second column is multiplied with the minus. That means directly we can write 0 iota, second column iota 0 minus, and whenever z is operating this side, this is the right side, or right side means rows. Okay, so same y, 0 minus iota 0, but you have to multiply row, second row with minus. This is a 0, no need. So directly you can write, so this is 0, 2 iota, and 2 iota 0, which is nothing but 2 iota 0, 1, 1, 0, which is 2 iota x. If you are not understanding, no need to worry, just directly multiply. So this is a small technique to write directly. Next, the most important thing, let us go and derive this. Okay, so this is very crucial. Now for this, we have to define this sigma I and sigma j. So I think they have taken sigma j, sigma k, because here we have iota. So that's why they have taken sigma j, sigma k. We'll take that also, that only. In the earlier, we have already discussed this problem. Okay, sigma j, sigma k. How to write this product? If both are same, identity. If both are not same, third one, we have used that Levi-Civita. Okay, so this is nothing but delta jk I. So I have already discussed earlier problems. If you go through the earlier somewhere, yeah, here, this one. I have explained in this problem 35. Okay. Right. So this is iota epsilon jk. Okay. You can take another index jkl, order jkl, something like that, and this is a sigma l. No, don't bother about this jk and all these things. And that tensor rotation, it is just a dummy index. Okay. Now this is our product of sigma j and sigma k. Fine. Now what we are going to find is you have to know the relation between this, I mean this one. This is the Kronecker delta and this is the Levi-Civita. So you just please remember like this. This is the JKL, write like this, JKL. So this is the cyclic permutation order JKL, KLJ, LJK. I repeat, all these values are plus 1. Epsilon, go in a cyclic like this order. So cyclic permutations JKL equal to epsilon, next KLJ, next epsilon LJK. All these are plus 1. If you go in the reverse order, so reverse order, we started from here, you can go in the reverse way like this. That is epsilon JLK, epsilon LKJ, epsilon reverse KJL. This is equal to minus 1. So basically if you go in the cyclic order, you will get a plus 1, and another order, you will get a minus 1. Okay, so this is a plus 1 order and this is a minus 1 order. Okay, now I'm going to take this sigma j, sigma k. So this is the commutator, sigma j into sigma k minus sigma k into sigma j. So by using this, I can substitute here. This is the directly delta jk I plus iota epsilon jkl and a sigma l. Then how to write this? No need to get tension. So minus as it is. Now this is a sigma kj. Whatever the order they have given, just take that order only. Don't worry about that. That means delta, whatever the order they have given, please take kj I as usual. No need to worry. Plus iota. Now Levi-Civita you have to write epsilon. I request you, no need to worry about this. Whatever the order they have given, just take that. What is the order? Kj. And the third one dummy index, just take L. That's it, sigma L. So now if you see carefully, and one most important thing, this Kronecker delta ij equal to delta ji. So these two are same. That's why these two gets cancelled. And already we have discussed here, jkl is a plus 1 and kjl is a minus 1. So these two are negative signs. I mean both are, one is a positive, another is a negative. So we can write like this, iota epsilon jkl sigma l, and here minus iota epsilon kjl sigma l. So I think this can be written as minus of epsilon jkl, because both are opposite in sign. So this is nothing but 2 iota epsilon jkl, this minus into minus plus, and a sigma l. Again you have to use that Einstein summation rule here. So if any index is repeated twice on one side, we have to take the summation. So that is 2 iota. This is L is repeated twice. That's why summation over L epsilon jk L sigma L. So this is the reason why they have not taken ij, because here iota is there. Maybe you will think it is repeated twice by using that Einstein summation rule. So that's it. And this is a very beautiful relation. Sigma j, sigma k commutator equal to 2 iota summation over L epsilon jkl sigma L. If you have any doubt, so please contact. Right? So we have discussed up to, second chapter up to 40 problems. And again, we'll meet again tomorrow. So if you have any doubt, so please contact. Thank you.